Good morning, class, and welcome to this lesson on circular motion on a banked curve. Circular motion on a banked curve. So today we are going to be able to determine the centripetal force when given a plane, a car, or an object attached to a string moving around a banked curve. So this is going to be conceptual in nature. We're not going to do any math today, but we are going to set up equations because that's really what the issue is here. Can we draw the free body diagram for this and set up the equation for it? Because that's 90% of the work before you start plugging numbers in. So just to be clear, you don't need to write these pictures down, but I just want to be clear, so I put these pictures up. This right here is a horizontal plane. And what's making the car turn is the frictional force. The frictional force of the wheels, when you turn the steering wheel, the friction points inward, and therefore the car makes a circular turn. Okay? So this is what we call, down here, this is what we call a banked curve. So, a banked curve is not, turning the corner in front of Wells Fargo near a bank. A banked curve means that the street is at an angle. So you can see here, this car is traveling around a banked curve. This is very common with racing, okay, like NASCAR and whatnot. So this car right here is traveling around a turn, which is a circle, on a banked curve. And so all the problems we're going to do right now, we're going to say there's no friction present. And when we mean no friction, unlike this situation right here, where the wheels are causing the car to turn, if this person just drives straight, with the wheel straight, the car will still turn. So this person in this car is not going to turn the steering wheel at all. If they keep the steering wheel straight, what speed can this person go to carry them around this turn without going up or down? Okay, so now if the person does turn the steering wheel, then they can go faster because there's now a second force present. But for right now, we're just going to consider no friction is present. This person is keeping the wheel straight. The only thing turning this car is going to be the normal force. So just to get that out there to clarify, this person is not turning the steering wheel. We are not going to consider any friction between the wheels and the street there. Okay, so you can see what our result's going to be this right here. But I want to go through that with you so that way you can see how it came about. Okay, so let's take a look here. You noticed from that picture that this car was sitting on a triangle, a banked curve. Okay, and this car, the dot will be considered by the car. Okay, so what forces do we have present? Well, we have gravity, and we have normal force. Okay, gravity and normal force. Okay, remember, centripetal force is not a force in itself. Centripetal force just tells us a force is pointing towards the center of a circle. So centripetal force is just pointing towards the center of a circle. It's not a force in itself. And let's just say this is going to be a 30-degree angle. Well, if that's a 30-degree angle, then this is a 30-degree angle. And I'm going to prove this to you two ways. Okay? Two ways. First way, let's pretend that this car was on a level road. This is going to be the car. And it was pointing, and so the normal force was pointing straight up. Right? Now, it is on a banked curve like that. And that is a normal force. And so you can see here that the difference, if I put that right there, that is the angle that it changed. Okay? It went from up and down to side. It changed that much. So that's 30 degrees. So that's just the angle of the curve. But let's just do it one more way to be safe. If I look at my triangle here, if I look at this whole thing right here, this is 90 degrees. This is 90 degrees. Okay, those are supposed to be perpendicular, so that's running all the way down perpendicular. If this is 30 and this is 90 right there, then this is 60. Okay, 30, 60, 90. Okay, that's common triangle. Well, if this is 60, then by, I believe it's alternate interior angles, geometry, then, sorry, this is 90 right there, but this right here is 60. And so if this is 60 and this is 90, then that has to be 30. Let me draw that again just to be safe. This is 60. If this whole thing is 90, if this is 60, then that has to be 30. Okay? So if we draw that down, just like we did before, if this is 60, then this is 60, and if this is 90, then this is 30. So you can see here that the angle is going to be, the angle here is going to be the same as the angle here. So no matter what we're given, those are our angles, okay? So let's continue on. How do we set this up? I'm going to clear this off now. Okay. Let's make sure we have a very clear picture before we move on, okay? mg, normal force. Well, what is pushing this car in? What is causing this to turn? Well, the normal force is causing it to accelerate, but remember, centripetal force points towards the center. So the centripetal force, I'm going to do a different color, centripetal force is going to be this right here. This component of N, okay? This component of N. I want you to notice that this is going to be the same as this. Those are the same. Let's get a different color. And that is going to be equal to that. Okay? So if this is our angle, we'll stick with 30. We'll stick with 30. Okay, if this is our angle, 30, right here, those are the same, then that means that this side is mg cosine theta. These are the same, so this is mg, wrong, n cosine theta, n cosine theta. This is n cosine theta, and that means that this piece right here is n sine theta, which is the same as this up here, n sine theta. So our centripetal force is n sine theta. So n sine theta equals mv squared over r. So that's our first way to set it up. That's our first way to set it up. A car on a banked curve, the centripetal force is this force pointing inward, and that equals mv squared over r. Okay? I'm going to take this one step further because this equation will pop up on you. Okay? I'll go back to this color here. Notice here that mg is equal and opposite to n cosine theta. These are equal and opposite. This car is not accelerating in the x and y direction, or excuse me, it's not accelerating in the y direction. Therefore, these are equal and opposite. So n cosine theta equals mg. Okay? Well, so what does n equal? Well, that means n equals mg over cosine theta. Well, why do I do that? Because if n equals this, and n sine theta equals mv squared over r, well, I'm going to plug n in there. So mg over cosine theta times sine theta equals mv squared over r. Okay? And just to simplify this, I'm going to divide both sides by mg. So I'm going to move the mg down this way, okay? mg over here. Sine theta over cosine theta equals mv squared over r mg. Notice the m's cancel out. And from trigonometry, remember that sine theta divided by cosine theta equals tangent of theta. So the tangent of theta equals v squared over gr. Okay? I show this to you because you might get a question and they're going to give you, they're going to set this up for you You might get a question, and they're going to give you the angle. We're going to have the angle. We're going to have all these different things. We're going to have how fast it's going. We're going to have the radius or whatever, and they're not going to give you the mass. They're not going to give you the mass. And so if you only set this up right here, you're going to be confused. You're going to think, I can't solve this problem because I don't have the mass. Maybe they're asking for the radius, and if you don't have the mass or the radius, how are you going to figure that out? Well, the reality is if you have this equation right here, tangent theta, well, you realize you don't need the mass. You don't need the mass, and so this is an important equation to memorize. This is an important equation to memorize because this equation helps us when an object on a banked curve, this is on a banked curve, and it simplifies it for us because the mass is canceled out. We have one tangent of theta. It becomes very, very simple. If we know the angle and we already know gravity, then we're solving for either velocity or radius, one of the two. Okay, so this is a very good equation to know. If I was you, as a student, I would start off with the picture again and see if I can do all this work to get to that point on my own, okay? That would be a very, very good study skill for you to have. Start off with the picture and work your way down to see if you can get that answer, okay? I just wanted to point out also two very similar problems. Notice here we have a plane. With a plane, we have something called lift. Lift is the force. Lift is just like normal force. Okay, lift is just like normal force, but it's for a plane. We didn't talk about lift with the four main forces, but it works the same way. Lift is just like normal force, and if a plane is traveling on a banked curve here, then the centripetal force is L sine theta. Remember before it was N sine theta, now it's L sine theta because we have lift instead of normal force. Same thing, same issue, except now it's lift. I want to do one more example for you. An object attached to a string attached to the ceiling. It is traveling in a horizontal circle. What is the centripetal force? Well, this is tension. This is tension, and the centripetal force is going to, actually let's draw this picture a little bit more. So that's the center of the circle, and so the components here, this component right here is centripetal force, and this component is gravity, gravity is the horizontal or is the vertical component of tension. So if this is our angle right here, which notice this, if I drew a line up from here, these two angles would be the same. These alternate interior angles, I think, I forgot. These two will be the same. So notice remember our car situation, like this. Kind of the same thing, same angles. These two angles would be, this would be T sine theta, this would be T cosine theta. T sine theta would equal mv squared over r, okay? And T cosine theta would equal mg, because T cosine theta, this is also the same thing. T cosine theta is equal and opposite to mg right there. So the math is going to work out exactly the same for a ball traveling in a circle on a string with tension as compared to a plane traveling in a circle with lift. Okay, I didn't write it out, but L sine theta equals mv squared over r. That's going to be L sine theta, which is the same as a car on a bank, n sine theta, because now we have normal force. The normal force is going to equal mv squared over r. These all work out the same way, but now you see that a car, normal force, is set up the same way as tension with a ball on a string, which is the same as a plane turning with lift.